Today we are going to finally learn about those trig functions that I've been talking about. Okay, and the first thing that we need here is our unit circle. Okay, the unit circle is a circle of radius 1. Okay, and you might have been able to guess that the word unit is oftentimes used for 1 in mathematics, with its center at the origin. We won't need this right away, but it's not a bad thing to know. The equation for a unit circle is x squared plus y squared equals 1. Okay. All right. So now that we know what the unit circle is, we can figure out what sine and cosine are. Okay. So you might have already noticed on your calculator that there is a button that is labeled SIN, one that's labeled COS. And that is because sine is abbreviated SIN. I know it's not much of an abbreviation, but that's what's used. And then cosine, the abbreviation is COS. Okay. All right, now to see what they are. Okay. So if you want to actually find cosine of theta, or you want to find sine of theta, well, you're going to first want to rotate off of the positive x-axis theta radians, okay, or theta degrees, whatever we're measuring it in. And where the terminal side intersects with the unit circle is going to actually give us what cosine theta is equal to in sine theta. Cosine theta we are defining to be the x-coordinate at that intersection, and sine theta is actually defined to be the y-coordinate of that intersection. Okay, and some of these points on the unit circle will be really easy to find. In fact, these next two that we'll do will be pretty straightforward. But there are many other angles where we're pretty much going to rely on our calculator to find the value, cosine or sine of those numbers. Otherwise, it would be extremely tedious, or we'd need a table. So we'll actually look at, we'll use all sorts of angles in this class, but you will notice that we will oftentimes stick with some of these common angles that you're kind of used to, like 30, 60, 90, 45, and their multiples. Okay, but let's give this one here a try. So it says sine of pi over 2. So the first thing you actually want to do is figure out where on earth pi over 2 is on this unit circle. Well, let me see if I can help you remember some of the easy points. So first of all, if we don't rotate at all, that's 0 degrees or 0 radians. Okay. And you might remember that a full revolution is 2 pi. So that might help us remember that then pi must be half a revolution. And that must mean that pi over 2 is up here at the top of the unit circle. Okay. And so I'm going to go ahead and sketch in my terminal and initial sides. In fact, I'm actually going to sketch in the initial side first here along the positive x-axis, and then here is our terminal side. Okay. And is what we really want with this terminal side again is just to know where it intersects the unit circle. Okay. Well, remember the unit circle is of radius 1, so if we're at the top of this circle right now, our y value must be 1 because it's again of radius 1, and since we're on the y-axis, x must be 0. So this is 0, 1. Okay. And is what that tells us then is that sine of pi over 2 is equal to one of those coordinates. And specifically, it's equal to the y-coordinate. So it's equal to 1. Okay. Let's try cosine. Okay. You can see that for this one, we're going to need to know where 3 pi over 2 is on the unit circle. Well, had we just counted one more pi over 2, that would have put us at 3 pi over 2 here. But all is the same. This is still pi over 2 and 0. And let's do that rotation. Okay. So here's our initial side, and here is our terminal. And we just need to know the x and y coordinate here. And we've lucked out. The x coordinate is again 0, and this time the y coordinate is -1 because we're at the bottom of the unit circle, and this circle has a radius of 1. Okay, so -1. And so cosine of 3 pi over 2 should be the x value here, so it should be 0. Now that we've finished up example 1, is what we're going to do is see if we can find sine and cosine of maybe angles that aren't on either the x or the y axis. Okay, so let's go ahead and go to the next page, and we're going to actually look at some triangles first. Actually, some triangles that you might be familiar with, and maybe you even know the side lengths. Okay, but I want to show you where those side lengths come from, because what we're going to do next is dependent on these triangles here. Okay, and let's start off with this 30, 60, 90 we have here. Okay, so you might actually want to pause the video for a second and see if you can figure out these sides without using, of course, sine or cosine or tangent. All right, so here's the trick. Okay, I'm going to sketch this exact same triangle, but reflected vertically. Okay, but it's going to be attached to this one. Okay, so I'm going to try and go down by what looks like the same length as the one up above. That looks about right. And then I'll come down this way. So if this green triangle is the same as this one up here, right? This would still be the 90. Okay. This one would be 30. This one would be 60. Okay, and I want you to think about this for a second. Now that you have this triangle here, can you figure out what the missing sides might be, or just a missing side, period, okay, of maybe a different triangle? Okay. So now that you've thought about it for a second, maybe you've figured out that is what we actually have here is an equilateral triangle. Okay, and that's a triangle whose side lengths are all the same. Okay, and now you might be wondering, well, how do I know that we've created an equilateral triangle here? Well, this is 60, this is 60, and if you add these two 30s together, you get 60. So if all three of the angles are the same, then all three of the side lengths must be the same. Okay, so what that means is, well, this must be a 1 here, and this entire length here must be 1. Okay. And so that's what I'm going to write in here. Since the hypotenuse of each 30, 60, 90 triangle is 1, we can conclude that the missing side of the equilateral triangle is 1. Okay, which is what we did up here. Okay, but we're not quite done yet. Okay, so if that entire side length is 1, then if you were to split it in half, you'd get a 1/2 here. Okay. So now we have the 1 and the 1/2. So we still have one more missing side. Okay. But that's actually not going to be too hard to find either. You might remember that a squared plus b squared equals c squared, where c is the length of the hypotenuse of a right triangle, and a and b are the lengths of the other, or of the two legs of the triangle. Okay, so let's go ahead and use this. Let's say that this missing side here that we have is a, okay, because this is a leg, this is not the hypotenuse. So we'd have a squared, and then the b here, the other leg, is that 1/2. Okay, and then c squared, well, c is 1, So we have 1 squared. Okay. So if you were to square 1/2, that's going to give you 1/4. So we have a squared is equal to 1 minus 1/4. And then that gives you a is equal to 3/4. Okay, and if you were, or sorry, not a equals 3/4, a squared equals 3/4. But if you were to then take the square root, or use the square root property, we're going to get a is equal to the square root of 3/4. Or how about the square root of 3 over 2? Okay, right, because the square root of 4 is equal to 2. Okay, so this missing side here, a, was the square root of 3 over 2. Okay, so now we have this thing filled in. One of the legs is the square root of 3 over 2, one is 1/2, and one of them is 1. Okay. Let's go ahead and try out this other triangle. Okay. So this is the easier one, in my opinion. This is the 45, 45, 90. Okay, and with the 45, 45, 90 is what we do know is that the two sides opposite of the 45s must have the same length. So let's just say that that length is x, right? Or it's an unknown length. Okay, but again, since or let me say one thing here that I haven't mentioned. So you might notice in both of our pictures here that we have used a hypotenuse of 1, okay? And that is because when we are done with this, we are actually going to be thinking about these triangles within our unit circle. So this would be the origin of our unit circle, and this would be the edge of the circle up here. Okay. So that's why they have both a hypotenuse of 1, is we're going to be on the unit circle. Okay. All right, but now that we know that, we can go on and we can figure out what both of these x's are. Okay, so they're both legs. So we have x squared plus x squared equals 1 squared. Okay, and you can actually rewrite this. If you have two of the same thing being added together, that means you have two of them. So 2x squared. And then 1 squared is 1. Okay. And then we have x squared equals 1/2. And then x is equal to the square root of 1 over 2. And I'm actually going to write this a little bit differently. Okay. So for one, you could rewrite this a little bit. You could rewrite this as 1 over the square root of 2. Right, because the square root of 1 is just 1. And then you could also actually rationalize the denominator. Okay, and when we do that, right, we're just really multiplying by 1 here. The square root of 2 divided by the square root of 2 is just 1. So we're not changing the value, we're just making it look different. Okay, this is going to give us the square root of 2. And when you do the square root of 2 times the square root of 2, it just gives you 2. So this is actually the way that we're going to look at the lengths of the sides of this triangle most frequently is the square root of 2 over 2 rather than 1 over the square root of 2. Okay. But we do need to be able to recognize that they're equivalent. Okay. But most of the time we'll see it again as the square root of 2 over 2. All right, and now that we have both of these triangles set up,